protocol on announcements before the seminar introduction. I do recall at one point we had a tradition of some announcements, etc. So any announcements? No? All right. Well, it's a great pleasure to welcome you all to this seminar with Dr. Shradda Dhungel, who is a postdoctoral fellow at the Environmental Defense Fund, which many of you would know is a major environmental organization that has been working for several decades on using science for basically developing mechanisms to hold corporations and other parties to account. And they have, in fact, a chief scientist's office, which is something that I think most NGOs should have. So having PhD level scientists working as postdocs is fantastic. And actually, I've had the good fortune of knowing the chief scientist of EDF, Steve Hamburg, for many years, and they do amazing work. So Shradda's joining them is a testament to her caliber and credentials as an applied academic. So she's got her training at Columbia University and is originally from Nepal. And she's going to talk about South Asia in the context of her research as well. And she's really an eclectic academic, very suitable for a geography seminar with multi-methods training. She's going to also present this seminar because we are hoping to recruit her as an affiliate faculty member, since she's in the vicinity also physically, and we hope that she will be able to serve on committees of graduate students, maybe also engage with some of our teaching, depending on her availability. But this seminar is also part of that process to have her affiliated in that capacity. So thank you, Shradda, for doing this and accommodating with your schedule. I realize you're moving this weekend also to a new apartment. And so thank you for doing this at a tough time. And feel free to add more in your introduction.
Thank you, Salim, for the introduction. Can you hear me clearly? Great.
Yes, very well.
Okay. Just a minor note. My postdoctoral experience was at NASA and Columbia, but my PhD is from at the University of Virginia. And thank you for the opportunity. Good afternoon, everyone. Today I'll be discussing briefly, like Salim said, about my research related to air quality and climate change in South Asia. Since this is my introduction to the department, I will begin my talk describing how I think about climate science research, mainly to pave the path to foster future collaborations within the department. During my PhD work at the University of Virginia and as a NASA postdoctoral fellow, I have looked at the implications of the increasing anthropogenic emissions and their impacts on South Asian regional air quality and climate. So before I begin my talk, I'd like to acknowledge my collaborators and funding sources that have contributed to the research that I will be presenting today. Anthropogenic climate change, its causes and consequences are not a new concept. I want to begin my presentation by briefly describing how I frame the current state of knowledge on climate change. I like to think about climate change knowledge in four different categories. The first category is the causes of climate change. We know that the rise in carbon dioxide and other greenhouse gas emissions is largely the result of human activities. These greenhouse gas emissions are leading to rising temperature and changing precipitation patterns. The planet is getting warmer and wetter. Anomalies connected to rising temperature and changing precipitation patterns like warmer oceans, increase in atmospheric water vapor, drier summers in semi-arid and arid landscapes are conducive for an increase in the intensity and frequency of extreme events. Climate change is providing an extra boost to extreme events, including effects on heat wave, drought, hurricanes, wildfires, and others. The second category of anthropogenic climate change knowledge relates to impacts. One major impact is expected to be the rising burden of disease related to heat, respiratory illness, malnutrition, and other foodborne diseases, to name a few. Another important impact is on agriculture. Climate change is expected to substantially reduce crop yields and change where crops can be best grown. Extreme events are also expected to contribute to frequent crop failures. So more broadly speaking, climate change is expected to impact the global economy. According to some estimates, by 2050, climate change is predicted to reduce economic output by $23 trillion compared with growth levels without climate change. Further, climate change impacts such as sea level rise and the effects of extreme events are expected to substantially increase loss of assets and lead to the displacement of communities. Then the third category of current climate change knowledge relates to solutions. The impact of anthropogenic climate change on the planet and the society have been extensively studied, and potential solutions have been put forth to address this challenge. Some of these include transitions to clean energy from fossil fuels, reduction in methane emissions, measures to halt deforestation, promote reforestation, and the restoration of degraded landscapes, along with a variety of other solutions. But despite this extensive scientific knowledge on causes, impacts, solutions, one of the most important remaining challenges is linking climate science with climate action. And it is this link that I consider as the fourth category of climate change knowledge. There are a variety of obstacles that continue to prevent solutions from being put into action. My talk today focuses on improving the understanding of anthropogenic emissions and its impact on regional climate with all four of these categories in mind. Like Salim mentioned, I am from Kathmandu, Nepal. So in addition to how I frame climate research, my interest in the field has been significantly motivated by my personal background. I was born in Kathmandu, Nepal, and I lived there until 2006. As a child, the Himalayan range was visible from the valley throughout the year. However, in recent years, due to the rise in local and regional emissions, one can rarely enjoy the same view of the mountains as they are frequently covered by thick haze. Another piece of evidence of climate change in context of Nepal is the shift in the onset and precipitation patterns of the summer monsoon. Roadways are increasingly damaged by flooding and landslides after torrential rain, while poor water and sewage treatment infrastructures are regularly inundated during monsoon. Low and mid-income countries like Nepal lack proper measures for climate adaptation and resilience, thus suffer greater human and economic loss due to extreme events. So seeing all of these changes firsthand has driven me to be a part of their solution. The effects of climate change versus the effects of air pollution happen at different spatial and temporal scales. Though these topics are linked intrinsically, delineating the impact of one on the other is complicated. For example, regional atmospheric chemistry can amplify the amount of radiative warming beyond mean rise in global temperatures due to climate change. The questions that motivate my research are a fusion of how I frame climate change science and my drive to benefit the people and places that are mostly vulnerable due to climate change. My research focuses on understanding the interactions between atmospheric composition and dynamics at various temporal and spatial scales, and how they influence climate outcomes. Secondly, what are the local and regional impacts of anthropogenic pollution, and ultimately seeking to understand how this scientific knowledge can be used to help inform decision making while prioritizing stakeholder needs. So now I will provide some examples of studies that I have undertaken to investigate the first two questions, and then I'll briefly discuss different ways that I have sought to interact with stakeholders and meet their informational needs. So the interaction between atmospheric composition and dynamics are closely interlinked. For example, changes in atmospheric composition due to increasing anthropogenic emissions causes rises in temperature and ultimately alters atmospheric dynamics. This leads to increasing rates of evaporation and an intensification of the water cycle. Alterations to the water cycle, on one hand, can contribute to more frequent and intense storms and increase the risk of flooding, while on the other hand, it can cause drying over some land areas and thereby decreasing precipitation intensity and increasing the risk of drought. Interactions between atmospheric composition and dynamics are evident in the global monsoon system, particularly in the South Asian summer monsoon system represented by the red box. This monsoon system delivers almost 80% of the total annual rainfall in the region during the summer season. It is a very important system given that the livelihoods of about 1 billion people are directly dependent on it for freshwater supply, agriculture, industry, hydroelectric power generation, and to meet their other basic necessities. However, rising temperature due to increases in anthropogenic emissions, both globally and regionally, continue to impact the South Asian summer monsoon precipitation pattern. Both observational and modeling studies have demonstrated that South Asian summer monsoon has weakened in the past decades. Some studies have focused on the role of rising emissions in causing these changes. Others have looked at the role of climate change, while others have looked at the role of intensifying agriculture, in particular expansion of irrigation and its net cooling effects. All three factors, rising aerosols, climate change, agriculture, intensifying agriculture, ultimately exert their own pressure on the South Asian summer monsoon by their influence on temperature gradient, atmospheric moisture availability, and circulation patterns. Yet, in the past, the influence of each of these factors on the South Asian summer monsoon have been quantified separately. But because we know that all these factors interact with each other in the real world, it is essential that we incorporate all three into our modeling efforts in order to gain a more accurate representation of what's actually happening. In order to understand the combined impacts of climate, anthropogenic aerosols, and agriculture simultaneously on South Asian summer monsoon, I use the GISS climate model E2.1, which is one of the CMIP6 models. It has a so-called star-shaped architecture where each component is separate from the other and is connected by a central coupler. The main benefit of this kind of model structure is that once it has been set, future changes to any of these components are relatively easy to incorporate. For example, an entirely ocean or land or sea ice component can be substituted very easily. One unique aspect of this particular model is the inclusion of irrigation, where it is prescribed as a time-varying parameter. So I ran this model from 1960 to 2014 to investigate how climate, aerosols, and agriculture are collectively changing the South Asian summer monsoon. First, we compared the simulated data with other data sets. The modeled precipitation amount does a good job detecting monsoon period, but slightly overestimates rainfall, especially during June and July, compared to the GPCP, which is the Global Precipitation Climatology Project data set. We also found that modeled average monthly temperature is in good agreement with MERA2 reanalysis data. The inset here shows how South Asia is defined within the model. So when I speak about a region, I mean the area within this box up here. So it includes much of India, Pakistan, and a little bit of the Middle East there. When we look at decadal precipitation average from 1960 to 2009, the model simulates a continuous decline in precipitation amount over the decades. The simulated trend shows a 20% decline in July and 16 in August, which are the two of the peak monsoon months. Thermodynamically speaking, this suppression of rainfall is likely due to several reasons. One is the weakening of the land-sea thermal gradient due to warming of the western and the southern Indian Ocean, and then a simultaneous cooling of the land surface north of it. Another reason for weakening rainfall may be due to large-scale deforestation to claim cropland and increasing evaporation for irrigation. We also found distinct spatial differences and changes in precipitation since the 1960s. The declines in precipitation are in blue, and the increase in precipitation or the positive values are in red. We see the strongest signals along the Western Ghats in India, the eastern coast of India, and over the Bay of Bengal. The signals of decrease remain strong along the Western Ghats of India until August. So this is June, July, August, and September. Another way to understand or calculate the strength of monsoon is using monsoon indices, which allows us to quantify the monsoonal strength. The one I used here is called the Dynamical Monsoon Index, which is calculated using the horizontal components of the wind at two different locations over the region. Here we're looking at 5 different model simulations. The gray one here is without global biomass burning. The yellow is without regional emissions. The blue here is without regional agricultural burning, and the green is without regional irrigation. The black solid line is the control. We see a general decreasing trend in monsoonal strength in the region across all simulations. However, the absence of regional agriculture, which is in green, and the absence of global biomass burning, that is in gray, are two simulations where the magnitude of the weakening of monsoon is the least, which suggests that both these factors play an important role in the weakening of the monsoon system. Another important factor is pre-monsoon surface temperatures that dictates the strength of the monsoon or even the development of the monsoon. Pre-monsoon surface temperatures are influence the monsoon through their influence on the land-sea thermal gradient. These temperatures are highest in the absence of regional irrigation because irrigation has a net cooling effect on surface temperatures. Given that the region has seen a rapid expansion in irrigated agriculture, especially as a result of the Green Revolution, it is not surprising that irrigation stands out as one of the prominent factors causing the decline and changes to precipitation pattern. As such, these modeling efforts point to the important role of sustainable and climate-smart agricultural practices in not only addressing anthropogenic emissions, but also cascading influence for regional climate patterns. These also highlight important feedback by which agricultural systems can affect themselves. Related to my first motivating question, I find that human activities and emissions, particularly irrigation expansion and global biomass burning, have been prominent factors leading to decrease in rainfall and weakening of the monsoon in South Asia, and that these climatic changes suggest effects on regional agriculture and the broader economy. Next, I want to provide an example of an observational study that I have done to investigate aspects of my second motivating question. What are the local and regional impacts of increasing emissions? I was specifically interested in investigating seasonal patterns of pollution transport, particularly to locations like the Himalayan range, far removed from places where emissions actually happen. This picture on the left is taken from an airplane, and you see this thick regional haze on the southern side of the Himalayan foothills. And this is a excuse me, this is a AOD map for the dry season from 2001 and 2002. So increasing emissions form a regional haze, which is technically called the atmospheric brown cloud during the pre-monsoon and winter months over the Indo-Gangetic Plain and the southern slope of the Himalaya. Here you can see the Indo-Gangetic Plain being delineated by higher AOD concentration here. And these features can be easily seen in satellite imagery. Most of the haze stays over the Indo-Gangetic Plain and tends to advect eastward toward Bangladesh as the Himalayan range blocks it from traveling further north. The composition of the brown clouds is dominated by short-lived climate pollutants like black carbon and precursors of ozone from sources like domestic combustion of biomass and biofuel, agricultural residue burning, vehicular and industrial emissions, to name a few. Even though this pollution seems to be advecting east, measurements at high altitude sites in the Himalaya and satellite-derived observations like this one here shows elevated concentrations of aerosols penetrating into the Himalayan valleys, where they can reach altitudes sometimes as high as 4 kilometers. So what does that mean in terms of regional impacts? The transport of pollutants like black carbon and ozone, which are both short-lived climate pollutants, can have a host of regional impacts upwind of pollution sources. One example is the atmospheric warming effect that they produce, which can contribute to the rapid melting of the snow and glaciers. Upon deposition, black carbon can also change the albedo or the reflectivity of the snow and ice surfaces and further cause melting. This picture here is taken 38 years apart. You can clearly see the effect of regional warming on the snow and ice cover on this mountain range. Black carbon and precursors of ozone, when suspended in the air like this, can change cloud droplet microphysics, thereby affecting cloud cover and precipitation pattern, and prevent the solar radiation from reaching the surface, all of which can have an impact on the onset and precipitation pattern of the monsoon system. Air pollution is one of the leading causes of premature mortality globally, and South Asia is among the regions most affected. Further, surface ozone interactions with the chlorophyll of plants. It interacts with the chlorophyll of the plants and reduces crop yields. In India, for example, crop losses due to ozone pollution have been predicted to be enough to feed 94 million people. However, given these many impacts, little is known about the transport pathways of these pollutants in the region. One example of this is the transport from the Indo-Gangetic Plain to the higher Himalaya. We investigated the role of Himalayan valleys to transport pollutants up to higher elevation by setting up 4 atmospheric stations along the Kaligandaki Valley in Nepal, which is one of the most open trans-Himalayan valleys connecting the Indo-Gangetic Plain to the Tibetan Plateau. This is a map of Nepal showing the location of the Kaligandaki Valley here. This is the zoomed in image from the same map where I'm showing the 4 stations that we had. All these 4 stations had at least one automated weather station. Zomsom had 2, one closer to the base of the valley and another one at about 3 kilometers up from the valley floor. This is an image taken from a commercial flight at cruising altitude where you can see the Himalayan range and this opening here, which is the Kaligandaki Valley. And this is the image of the field site at Zomsom, where we had not only an automated weather station, but also a black carbon and an ozone monitor. So we categorized our observation into pre-monsoon, monsoon, and post-monsoon seasons as differing sources, sinks, and meteorological patterns dominate seasonally. For the station furthest up the valley, we found that black carbon and ozone concentrations are highest during the pre-monsoon season. Concentrations were lowest during monsoon season when there is active wet deposition of pollutants, and then started to build up again in the dry season. The concentrations recorded during the dry season are especially high, given that the station was located in a remote valley with limited local emissions. Then we looked at the flux of black carbon based on wind direction. In my previous slides, I had mentioned that we had 2 locations, one at the base of the valley and one at the top of the valley. And what we did was we used the wind speed and wind direction from those 2 places to calculate the flux that would go through that plane, if you can think of it, that cross section of the valley, to see how much black carbon is actually being transported up the valley. And we found that during daytime, when the wind flows up the valley and away from the Indo-Gangetic Plains, as much as 38 micrograms per meter cube or meter square of black carbon is transported every hour. Now, keep in mind the number 38, as it will provide you more context in the next slide. So these dashed lines here, the green one is ozone concentration, the black one is black carbon concentration. These dashed line, the black and the green, are they show WHO air quality standards above which exposure to black carbon, which is a constituent of PM 2.5, and ozone are considered unhealthy. So that is above 30, about 30 microgram per meter square, which we saw in this previous slide as the flux of black carbon that was going up the valley. So in another we also examined episodes of extreme pollution transport, which tended to occur right before the onset of the monsoon season. The black carbon concentration reached as high as 70 micrograms per meter cube, and ozone concentrations were reached as high as 80 parts per billion by volume. Based on this, our estimates also suggest that during an extreme pollution event, several metric tons of black carbon could potentially be transported up the valley, with obvious implications for glacial melting and respiratory and cardiovascular health in and up the valley. For my research on pollution transport, I have also used airborne measurement techniques like ozone sondes and instrumented flights to understand the impact of stratospheric ozone on lower troposphere, and also the vertical distribution of aerosols along the southern slope of the Himalaya. So related to the second question, I've shown that mountain valleys play an important role in transporting pollutants to higher elevation, with important consequences for glaciers and the regional water cycle, and that extreme pollutant events bring large amounts of pollutants up valley, especially during the dry season. And in addition to the effects on glacier snow melt, these findings suggest that this pollutant transport will likely also affect regional rainfall, health, and agriculture. So next, related to my third motivating question, I'll briefly discuss the ways that I have sought to interact and engage with stakeholders in order to understand their information needs and priorities related to climate change. The first of such example is my work with ICIMOD, which is an intergovernmental organization that works with countries that share the Hindu Kush Himalayan region from Afghanistan to Myanmar, including China. The headquarters are in Kathmandu, where I was a visiting researcher with ICIMOD's Atmospheric Initiative Group, and worked on multiple campaigns to foster scientific collaborations and link research to inform decision-making and science communication. I'm also part of the 100 Questions Initiative's Air Quality Group through World Research Institute and New York University, working to identify the next generation of pressing societal questions related to rising industrial and residential air pollution and their potential solutions. This group involves wide collaboration between scientists and stakeholders and seeks to inform climate-friendly investments. Additionally, I'm involved with the steering efforts of the Yulins Education Foundation in Nepal, which is seeking to establish the first liberal arts college focused on sustainability and governance. It has given me an opportunity to provide climate expertise in shaping the vision and curricula at the university. Next, I will just briefly mention my current research. In addition to my ongoing work at NASA GISS investigating the South Asian summer monsoon, currently at EDF, I am looking at linkages between various methane mitigation pathways. Methane, as you know, is another short-lived climate pollutant, and its impact on future extreme events, human health, particularly concerning with PM 2.5, and food security. Broadly speaking, I am interested in quantifying the social impacts of climate change, air pollution, and extreme events, investigating the role of mitigating short-lived climate forces in meeting near-term climate goals, and collaborating with cross-disciplinary experts to identify feasible pathways to putting climate solutions to action. And with that, I would like to thank you for your time and for inviting me.
Thank you so much, Shradda. That was very comprehensive, and you bridged some very timely topics. As you know, I am originally from Pakistan, and with the recent floods, there has been so much speculation on is this related to extreme weather events that are occurring with the western movement of the monsoon. So one immediate question I would have for you is, your data is suggesting that actually precipitation is going to decline with climate change and also with irrigation. How does that sink in with this kind of current situation in the western parts of South Asia? And also because there was a science paper, I think just 2 weeks ago, which suggested that the floods were linked to climate change.
Yes. So the South Asian monsoon system itself is weakening and the amount of precipitation is changing. But how and when these precipitation events will occur and how intense each of these are going to be are as an effect of climate change is what happened in Pakistan. Like two once in 100-year events, rainfall events happened back to back within 3 days, where the attribution studies that have came after that flooding event has shown that 40% of or 40 or 50% likelihood of that event being the result of climate change. So I think it's a two-layer thing that is happening where the drier western part of the South Asian monsoon region is getting this sporadic and intense rainfall where we see this shift, but as a result of climate change on top of whatever is happening regionally.
Okay, great, thank you. So in terms of the questions, if anyone wants to answer them at the plenary level, just go ahead and do so. If it's on the chat, Nancy, if you can moderate the chat questions.
Sure. I have a question, if it's okay if I go first after Celine.
Please do. Yes, please, Tracy.
Yeah, I was really curious about the irrigation modeling work that you talked about, Shradda. Can you talk about how you modeled the irrigation in terms of that area to be able to look at what the response of the climate was?
So irrigation itself in the GIS model is a prescribed variable, and it has, depending the data set increases with the year in conjunction with how water demand has changed in that region. And the way I looked at irrigation on top of what I showed as just the surface level, the surface temperature change, we also looked at the Bowen ratio to look at what is being evaporated and how much of surface cooling is actually happening. And we do see a distinct pattern in the decrease in surface temperature, even with the Bowen ratio calculations, to see that irrigation actually has played a very big role in that region. And you kind of see that change like 1965 or 70 onward when the Green Revolution actually occurred in that region.
Well, thank you. Yeah, it was really interesting to look at that graph that you showed in terms of time and how the model was affected in terms of the irrigation. So thank you.
Thanks, Tracy.
Okay, other questions? Shradda's research spans some of our climatology work. Also, we have a course on air pollution and meteorology, which Christina Archer currently teaches. So we've got a lot of intersectionality here with the work that's happening at the department. So hope others will join in on questions, discussion.
I have a question as well. Can you hear me?
Yes, please.
Okay. So when you were talking about the limits for black carbon and ozone going into the higher latitudes, what was the organization that set those air quality standards?
World Health Organization.
Okay. And then like, was there any kind of like aftermath after this research was published to kind of hold, I don't know, polluters accountable for that?
That's a very tricky question in terms of like, how do you hold people in countries accountable? Unlike people that require visa to travel from one country to the other. I was an international student throughout my school life, so I understand like the whole visa thing and how like air pollutions don't need that. As long as the air carries it, it's like transboundary that it can migrate from one place to the other. When you look at when these events occur, most of them occur when there is a lot of agricultural burning that is happening in the Punjab region of Pakistan and the northern northern India, along with forest fires and agricultural burning in southern Nepal. So to pinpoint where one part, it's a little tricky situation, but air quality has been in the forefront for at least for India for the past 8 or 9 years since that New York Times article came out showing air quality levels in India, in Delhi particularly, being one of the worst. So the sources from where these the sources of these emissions are a central part of talks just in India at a federal level. So hopefully we can see that being mitigated and result into some actions.
Thank you.
You're welcome.
I think Dan had his hand up.
Yes, Dan, please.
Which Dan? This Dan? I didn't have my hand up, but I do have a question that I'll ask. I just wondered, I'm very interested in snow cover and how that affects the climate system. And certainly there's been a lot of work done in years past on snow cover and its role in the monsoon. How does that play into your research at all, or how was that at all taken into account? I assume that the model itself, I saw that it had land ice, and I assume it had snow cover and so on. I just wondered if you could maybe comment on that a little bit.
And Shradda, for your sort of information about introducing our colleagues in the department, Dan is the state climatologist also, and has been former chair and teaches a lot of our core climatology courses and advises graduate students as well.
Yeah, I've had the opportunity to meet Dan a couple of years ago.
Yep, we did. Yep.
In terms of the model itself, what I'm looking at, I am looking more into the precipitation cycle and the onset of monsoon. And I haven't looked at snow cover and how that influences it. However, I am aware of the theory about about weakening of the high pressure system that is on top of the Tibetan plateau that kind of leads the thermodynamics of like the airflow, and which determines the strength of the monsoon season is weakening just because of the presence of radiation absorbing aerosols like black carbon along the southern slopes of the Himalaya, where you're not getting the temperature or the pressure gradient, enough pressure gradient at upper level that influences that has been influencing the monsoon.
Yeah, and so the model is kind of at least kind of implicitly taking that into account or not when it is? Yeah.
Yes, it is.
Okay.
It is,
Yep.
but I'm not focused on
On that.
the snow aspect of it. I'm more into the thermodynamics and how
Right.
atmospheric chemistry drives the dynamics.
Yeah. Okay. Cool. Thank you.
Thanks, Dan.
I have a question related to the precipitation map that you showed of and that there was one of the worst areas affected by more precipitation was the Chittagong hill tracks area, as well as the Chittagong area. And I understand that there is there are deforestation issues there, and then especially as that especially the Chittagong hill tracks are switched from call it indigenous slash and burn agriculture and land lying fallow to more agribusiness, which would be consistent farming of the same area. And I wondered if you find good sources of information that show to what extent there's soil erosion exacerbated by climate change and increased precipitation.
One of the limitations of using the climate model is the resolution of it, where I am looking at 1 degree by 1 degree that I haven't seen, or even I haven't looked at how land use has changed in those regions. So I'm not sure. I'd have to look into it as for why it has been increasing. What is causing that decrease in along the Western Ghats, like you mentioned?
Great. Appreciate that. It's a big area that you're looking at.
It is.
I should also mention, Shradda, one of our reasons for interest in the Chittagong Hill Tracts is we currently are working on a project which is looking at the connection between land and resources on peace and conflict. And the Chittagong Hill Tracts is one of the case studies that we are using, and Nancy and I and one of our PhD students is working on that currently.
Yeah, interesting.
Okay, other questions, comments, anything in the chat, Nancy? Right. Okay, now we usually have some time for graduate students separately with the speaker. So Nancy, if you can just check to see what's the graduate student attendance, and then they can continue on the Zoom while the faculty exit.
The graduate student attendance is very impressive. So,
Okay, very good.
and
Well,
I'm not,
that's excellent.
Yeah.
So then I guess we will then thank Shradda for this part of the seminar with also the note that this will be available. The graduate student part we won't record, so our friends who are doing the recording in the AV system, they can stop the recording now, and then please send the recording file to April English for upload on YouTube. And then the graduate students can have a more informal time with Shradda as we exit with gratitude.
Thank you, Shradda.
Okay.
Thank you, Shradda.
Thank you so
Thank
much.
you all.
Yes.
Talk.
Yeah.
Thanks, Shradda. Bye.
Okay. And please make the Zoom link should remain active. So whoever has to be the host should continue to be. I'm not the host, so I don't know. Whoever is, please make sure it's active. All right. Thank you. Bye.
Thank you, Salim.
Oh, this is Richard from the University of Delaware. Please contact Stacy here at the university, and we'll find out who needs the video. Okay. Thanks. stop the recording now.